Hello. In this lecture, we're going to continue talking about buffers. I want to do another example of a calculation involving a buffer solution. And in this example, we're going to take 1 liter of solution, aqueous solution of course, that's prepared with a combination of acetic acid, 0.1 moles of acetic acid, so its formula is CH3COOH, and 1.50 moles of sodium acetate, which of course is the salt of the conjugate base of acetic acid. I'm going to tell you that the Ka of acetic acid is, you probably have this memorized by now, 1.8 times 10 to the minus 5. That's a value that we use quite often. Okay, this is going to be a 3-part calculation. And in the first part, I just want you to calculate the pH of this solution. Okay, so it's an aqueous solution, and whenever we are tasked with calculating the pH of an aqueous solution, we have to look what's in the solution and see what's going to be controlling the pH. Now, here we have a weak acid and the salt of its conjugate base. So that should give you a big warning bell that this is a buffer. How do we calculate the pH of a buffer? Well, we use the Henderson-Hasselbalch equation, of course. So I'm going to abbreviate that, the HH equation, which we derived in a previous lecture. The pH of a buffer can be calculated as the pKa plus the log of the concentration of base, which in this case is the acetate, over the concentration of its conjugate acid, which in this case is the acetic acid. So this will enable us very easily to figure out the pH of this solution. Now, we were given molar quantities, but we were also told that the total volume of the solution is 1 liter. So it's going to be 0.1 molar in acetic acid and 0.15 molar in sodium acetate. So we can plug those values in to the Henderson-Hasselbalch equation. The pH of this buffer solution is going to be equal to the pKa, which is the negative log of 1.8 times 10 to the minus 5, plus the log of the concentration of base, which is 0.150 molar, over the concentration of acid, which is 0.1 molar. This is equal to, that pKa comes out to 4.74 plus 0.18. So you'll notice that the pH of this buffer is 4.92, and this value is just slightly above the pKa, which makes sense because we have more base than acid, right? We have more moles of base than we have moles of acid, which raises the pH to a value slightly above the pKa of that buffer. So this buffer solution has a pH of 4.92. Let's add a second part to that question. So in a typical buffer calculation, we might be asked to calculate the pH after 0.020 moles of HCl are added. Of course, HCl is a strong acid. Usually in problems like this, we're told to assume that the volume doesn't change. So assume no change in volume. Now, what happens when we add HCl? So HCl, of course, is a strong acid. And that is going to react with the base component of the buffer, the weak base part of the buffer, which of course, in this case, is acetate, the conjugate base of acetic acid. Let's write a reaction showing what happens when HCl enters that solution. HCl reacts with the base component of the buffer. I'm leaving out my aqueous species indicators. Now, since it's a strong acid, this reaction is not equilibrium. It goes to completion. And that strong acid protonates the weak base to make its conjugate acid, acetic acid. What's left over after HCl donates that proton is just the spectator ion chloride, right? Chloride, you remember, is a non-base because it's the conjugate of a strong acid, so it doesn't have any interesting acid-base properties. Now, this is not an equilibrium reaction, but as in the last lecture, I want to make an ICF chart to kind of show what's happening here. So at the beginning, let's just assume we have, we have molarities, right, because we are not changing the volume of the solution here. At the beginning, I had 1.50 molar acetate, and I'm adding 0.020 molar HCl because I assume no change in volume. I also had 0.100 molar acetic acid at the beginning. Chloride I don't care about because it's not going to affect the pH of the solution. So, do I have enough acetate to consume all of the added strong acid? I sure do, right? This number is much bigger than this number. So I can subtract, let me change the color here, I can subtract this number from the number of moles of acetate to get a final concentration of acetate, which is 0.130 molar. This will wipe out all of the strong acid that I added. However, on the opposite side, I'm going to have a corresponding increase in the conjugate acid, acetic acid, so that its final concentration is going to be 0.12 molar. Now, after this reaction happens, the buffer doesn't re-equilibrate. This is the new normal for it. So now it's still a buffer. Notice that we still have both the weak base and weak acid pair. So it's still a buffer at the end. So what do we use to calculate the pH of a buffer? The Henderson-Hasselbalch equation. So let's plug these new concentrations into the Henderson-Hasselbalch equation and see what changed. So I have the pKa that I calculated from before, 4.74, and now I'm taking the log of base over acid again, but the ratio has shifted slightly, right? I have 0.130 molar over 0.120 molar. So this ratio is much closer to 1 now, so that pH is just ever so slightly above the pKa, because I still have just a little bit more of the base than I have of the acid. So this pH is just ever so slightly above the pKa of the acetic acid acetate buffer. Now I want to show you kind of how dramatic this is, just to give you a quantitative idea. If I had 0.02 molar HCl and just added to water, this would give me a pH of below 2. So you can see the power of the buffer in modulating the change in pH when I add a strong acid. Okay, let's add yet a third part to this buffer calculation. I want to see what happens when I add strong base. So calculate the pH after 0.02 moles of hydroxide are added to the original buffer. So this is added to the buffer from part A, not from part B, but from part A. So to the original buffer from part A. Again, assume that there's no change in volume. Just like I did in part B, I'm going to assume no change in volume. So I'm just adding a negligible amount of volume. Okay, so what happens here? Well, let's think about what's going to happen. OH minus is a strong base. And a strong base is going to react with the acid component of the buffer. So the weak acid part of the buffer, which of course is acetic acid. So that's CH3COOH. Let's write a reaction that shows what that looks like. OH minus reacts with the acetic acid part of the buffer. Now, the base functions as an electron, as a proton acceptor to make water, and acetic acid gets deprotonated to make acetate. So if I want to quantify what's going on here, I'm going to make an ICF chart underneath this. I'm starting out with, in the original buffer, I have 0.1 molar acetic acid and 0.15 molar acetate. I'm adding 0.20 molar hydroxide, and I don't care about water because it's not going to affect the pH of the solution. Now, this number is bigger than this number, so I'm going to definitely have enough acetic acid to consume all of the added hydroxide. And it's just going to decrease the concentration of acetic acid to 0.08 molar now instead of 0.1. And I'm going to have a corresponding increase on the other side of the weak base concentration. So the acetate concentration after this reaction is going to be 0.17 molar. Is it still a buffer? It absolutely is, right? At the end of this, I have a weak acid, weak base combination. And as long as I have both of those two components, it's a buffer. So I can use the Henderson-Hasselbalch equation to figure out what the pH is. So the pH is going to be the pKa, once again, which doesn't change. It's still 4.74. Now the ratio of base to acid is bigger. I have 0.17 molar base and 0.08 molar acid. And that's going to mean that my pH is going to be bigger than it was before. So adding the strong base hydroxide raised the pH of the buffer to 5.08. However, it's not that big of an increase because the same hydroxide addition to just plain water would give a pH of 12.3 or so, which is enormous compared with 5.08. So once again, we see the power of a buffer to prevent drastic swings in pH. Okay, so now just to finish the segment on buffers, I want to talk about some practical considerations that we should all make when we're in the laboratory. So if we are going to prepare a buffer, you have to consider primarily three main factors. First of all, every buffer has an optimal range, the effective pH range in which it works the best. So I'll talk about that in a minute. We also should think about the capacity of the buffer and whether we're going to exceed that capacity. So buffer capacity really is how much weak acid and weak base we have so that we can figure out how much strong acid or strong base can be added effectively without wiping out the buffer components, the weak acid, weak base. So without wiping out the buffer components. That's really important because once you add so much strong acid or strong base that you are wiping out the buffer components, then you have exceeded the buffer capacity. And of course, the final consideration, which I believe I've mentioned in a previous lecture, is that the buffer must be inert, chemically inert, so that it doesn't produce undesirable side reactions. Okay, so let's talk about the buffer range for a second. For the buffer range, the best pH for any buffer system is when the pH is approximately equal to the pKa of the buffer components, or the pKb if you're looking at a weak base primarily. You want, so what this means, if the pH is around the pKa, you want the weak acid to be approximately equal to the conjugate weak base concentration. So you want these concentrations to be similar so that the pH is as close as possible to the pKa. And of course, I could say or vice versa. The weak base should be about equal to the concentration of the concentration of the weak base should be approximately equal to the concentration of its conjugate weak acid. You see this in action often in the laboratory when you use a pH indicator. So indicators are actually buffers. So pH indicators, like phenolphthalein for one. These are good examples of buffers. So let's say I have an indicator. I'm going to just call it HA. This is a weak acid, generic expression for a weak acid. Let's say it's an indicator, and let's just say it's one color. I don't care. You can imagine it's purple. When it gets deprotonated, you get its weak base, and that's another color. So color indicators are, color indicators are just going to be species that change in color when they get deprotonated or protonated. So this is going to be another color. So the deprotonation in this case would give you an indication of a change in pH. So you can just think about this kind of using the Henderson-Hasselbalch equation, right? Because for the Henderson-Hasselbalch equation, of course, the pH equals pKa plus the log of the concentration of weak base over the concentration of weak acid. And if you're actually doing a titration, which we'll talk about in the next lecture, when the color of the indicator just changes, so that moment when it just changes, that's when the pH is equal to the pKa of the indicator. Therefore, you want to choose an indicator that has the pKa, you want to choose an indicator for which the pKa equals the pH at what we call the equivalence point. We'll talk about that a little bit more in the next lecture. So I'm going to spend the subsequent lectures talking about titrations. I hope that you enjoyed this lecture, and I will see you for the next one in which we will discuss acid-base titrations. Bye-bye.